In this video, we're going to look at how we can convert numbers between different base systems. So, for example, how can we convert a number from base 5 to base 17, should we need to? Now, we've already looked at how to do this when going from base 10 to binary by using the iterative integer division approach. And that approach can be generalized to convert between any base. We're going to review that in this video. But before we do that, I'd like to start by looking at some circumstances where we want to go from base A to base B, and because of the relationship of those bases, we can actually do it a little simpler and maybe a little quicker. So let's start with trying to convert something from hexadecimal to octal. We'll use a string from a number from a previous set of slides. So let's take the value hex I think it was 3E7, I think. Hex A3E7, and we want to convert that to octal. Now, the nice thing here is that hex, this digit, this number is a hex number, but hexadecimal in general is base 16. And base 16 is the same thing as 2 to the 4th. Octal is base 8. And 8 is equivalent to 2 to the 3rd power. So each of these two bases that we're working with have a common root, 2. As a side effect, that means that we'll be able to convert between the two using the common root. So what we're going to do is put in the middle of these guys the common root, which is 2 to the 1st power, or 2. So we're sort of going from each to and from base 2, which is binary. All right, so that means the first thing we're going to do to get A3E7 in binary is convert A3E7 to octal, is we will convert it to binary. Now, if you recall, each hexadecimal digit, because it's 2 to the 4th power, is really a set of binary digits, so a set of bits, 4 bits in particular, so 1 nibble. Each hex digit, 1 nibble. So all we need to do to convert to binary is take this A and figure out what the binary for A is. Now, A, if you recall, is the coefficient 10. So we're going to do 10 in 4 bits. So that's 8 not plus 4, because that would give us 12. And the next digit down would be worth 2. So 8 plus 2 will be 10. And then in the ones digit, we'll leave a 0. So I'm going from the highest ordered bit down to the lowest as I fill these out. Remember, so 8 plus 2 is 10. I'll do the same thing for each of these. 3 in 4 bits is 0, 0, 1, 1, because that's 2 plus 1. And E is 14. So 14 is going to be 8 plus 4 is 12, plus 2 is 14, and so we must not need any other bits. Then we need 7. So 7 is going to be 0, 4, 2, and 1. 4 plus 2 plus 1 is 7. All right, so we've come up with this long binary string, and we're on our path to converting our original value to octal. So now what we need to do is recognize that in octal, for every octal digit, there are 3 bits associated with it in a binary representation. So what we'll do here is, starting on the right-hand side with the least significant bits, we're going to identify each group of 3 bits as we move to the left. There's 3. There's another 3. Here's 3. Now, I got 1 bit left, but realistically, it's just as good as 3 bits with some mysterious ghost zeros in the front. So we really do have an extra 3 bits leading this. So now what we want to do is represent each of these 3-bit patterns as an octal digit. And since octal is base 8, it has coefficients from 0 to 7. So we'll start with this one. This will be this is the 3-bit version of the number 1. This is the number 2. This is the number 1 again. This is 4 plus 2 plus 1 is 7. This is 4 and nobody else, so 4. And this is 4 plus 2 plus 1 is 7. So each of these little clusters of bits is connected to a single octal digit in our answer. And that lets us convert from hexadecimal to octal. Now, we may want to do the exact opposite. We may want to take an octal number and reinterpret it as its equivalent hexadecimal value. So we need to do that as well. But we can do it in the same fashion by going from octal to binary, and then from binary back up to hexadecimal. So let's do that. I think on the same set of slides we had a different number. So what was it, 527, I think. So let's take octal 527. This is the way we would write it in C, but I'll put a little subscript here to let us know that it's octal. And we won't really care about this 0 in the front. I just do that out of habit for programming in C or C++. And I want to convert this to hex. All right, now remember again that octal, which is base 8, 8 is 2 to the 3rd power. And hexadecimal, which is base 16, 16 is 2 to the 4th power. And their common root is the 2. So to go between them, we will go to base 2. So I'm going to go from this octal value here, 527, to binary. And then I'm going to do it the same way. So we're going to convert 5, and then 2, and then 7 each individually into 3-bit patterns in binary. So 5 in 3 bits is 1, 0, 1. That's 4 plus 1. 2 in binary is 0, 1, 0. 7 in binary is 1, 1, 1. 4 plus 2 plus 1 is 7. So now we've made the initial conversion from octal to binary. But we need to go from binary now to hexadecimal. In hexadecimal, each hexadecimal digit is worth 4 bits of binary. So I'm going to start on the right-hand side with the least significant values and underline each cluster of 4 bits. So there's 4 bits. Here's the next 4 bits. Then again, I have one remaining bit, but we'll just assume there are a bunch of leading zeros here for us before we solve this problem. All right, so for each of these 3 clusters of 4, each of these 3 nibbles, I can now write the equivalent hexadecimal value. So the hexadecimal associated with the number 1 is actually 1. The hexadecimal associated with 0, 1, 0, 1, well, that's 4 plus 1. This is 5. And the hexadecimal here in these 4 bits will be 4 plus 2 plus 1. That's 7. So we can say we've got hex 157, where each of these came from the nibbles above. So the reminder then is that if you are converting between bases that have a common root, then you can convert down from your first to that root as a new base, and then go back out. Now this is particularly easy if that root is 2, because it's pretty easy to convert to binary. Division by 2, even mentally, is not so hard. But this same rule of thumb applies in other bases as well. So let's try to take a value from base 5, let's say. And we won't give that a name, we'll just say it's base 5. And we want to convert some number that's in base 5 to base 25. Okay, so we just need some kind of a number in base 5. Recall that because the base is 5, the coefficients will go from 0 to 4. That's 5 different coefficients. So let's do 4, 2, 1, 4, 0, 2. At the very least, we can say this is a base 5 number. Now we want to convert this base 5 number to base 25. And so we're going to check to see if they have a common root. Now 5 is a prime, and so it's basically going to be 5 to the first power. Base 25 actually is 5 squared. 25 is 5 squared. Now they do have a common base, and one of them is the common base, which means to convert from base 5 to base 25, I don't have to go to an intermediary base. I can actually just go right from base 5 to base 25, because for every 2 digits in the base 25, every 2 digits in the original base 5 number, I will get 1 digit in base 25. The only problem, of course, is that my base 25 number is going to have coefficients that are unusual, because it's going to be coefficients from 0 to 24. Now in hexadecimal, we have coefficients that go from 0 to 15, so it doesn't sound that crazy. And what we do in hex is once we get past 9, we represent the coefficient value of 10 using the letter A, and the coefficient of 11 with the letter B, and so on. So we can just do the same thing here with letters of the alphabet. So in base 25, we'll say each digit is 0 through 9 for the first 10 coefficients, and then A on up for the remaining 15. Okay, so let's group our low base digits together, starting again from the right. So I'm going to need 2 base 5 digits for each base 25. So we're going to highlight these two, and these two, and these two. So that one worked out nice and evenly. Now we got to convert between them. Okay, so we need to know what the base 25 equivalent of 4/2 is in base 5. So to do that, we'll have to recall the basics of positional numbers. So this really means the coefficient of 4 times 5 to the first power, because this is the 0th position and the first position of this 2-bit sequence. So that's 4 times 5 to the first power plus 2. I'm only writing this out just to make sure that we totally see it. And that's 2 times 5 to the 0th, but I won't write that. That's 1. So this is really 22. Okay, so we need 22 here. This is 1 times 5, which is 5, plus 4. So this one here is worth 9. Then we have 0 times 5, 0, plus 2 is 2. So to write this, we have 2 of the 3 digits we need, but it appears we have a 2-digit value here. Now it's only 2 digits because this is really the decimal equivalent. So what we need is the base 25 version of this value. Now, one way you can get this, we're looking again for what 22 is in base 25, is you could start with A being 10, and then count up to B being 11, and keep on going until you reach whatever happens to be the letter that's associated with 22. But if you're anything like me, you'll keep a little decoder handy for such circumstances. I keep mine discreetly hidden in a scented orange zest sachet. Now, this lists all the letters of the alphabet where A starts at 0, not 10. And this is because I can use this secret decoder for a number of different things. But I do know that relative to the beginning of the alphabet, A is in the 0th position. So if I am looking for the 22nd digit in base 25, I know the first 10 digits are 0, or first 10 coefficients are 0 through 9. So A is 10. So all I got to do to figure out what these values are relative to 22 is just add 10 mentally to these. So I'm looking for 12, which is here. So I know that 22 is really M. Back to the sachet. So this is M9. 9, 2, and base 25. All right, so that's the basics of how we convert between things that have common roots. But what about converting between bases that appear to have nothing to do with one another? And whether or not they actually do, you just maybe don't notice their relationship. So we need a more generic approach to convert between arbitrary bases. We're going to do that using the same repetitive integer division process that we've seen before. So let us try to convert between a number in base, say 7, and we'll go to base 3. Now this will be nice because we can tell for sure that these don't have any common roots because each of these two bases are prime numbers. So the way we're going to have to do that first is take whatever value in base 7, convert it into base 10, and then we can have a number that we're ready to do the iterative division on. So first, let's get a base 7 number. How about, well, the coefficients for base 7 numbers will be between 0 and 6. So 5, 3, 0, 6. That's certainly a base 7 number. So let's figure out what this number is in decimal. We'll convert it by using the complete coefficient base exponent form equation. So the 5 will give us 5 times 7 to some power. This is the 0, 1, 2, 3 position, bit or digit 3. So this is 7 to the third power, which is 49 times 7 is 343 times 5 is 1715. Add to this a 3 multiplied by 7 in the 2's position, so 7 squared. I know it's 2 because it's 1 to the right of the third exponent position. We'll skip the 0 coefficient. Oh, well, let's solve for this guy. So 7 squared is 49, right? And we want to multiply that by 3, and that is 147. Yeah, 3 less than 150. 147. Add to this, well, this is the 1's position no matter what the base is, so this is really 6. So we'll add 6 to that, which gives us a final decimal answer, 1868, I think, base 10. So 5306 base 7 is equivalent to 1868. Now we want to convert 1868 to base 3 to complete the whole thing, and so we can just use the iterative division method. So we're going to find a bunch of quotients and a bunch of remainders here. This is a relatively large number for base 3, so I'm just giving myself a nice bit of room for all the different quotients and remainders. First, 1868 divided by 3. 18 divided will give us the 600, and this would be 66 to 22, so 622 with a remainder of 2. 622 divided by 3, obviously the 2 here, and then this is close to 21, so that'll be 7. So 207 with a remainder of 1. 207 divided by 3 is 69 even. No remainder. Those are both multiples of 3, so we get 23. Remainder of 0. 23 divided by 3 is 7 with a remainder of 2. 7 divided by 3 will be 2 with a remainder of 1. And 2 divided by 3 will be 0 with a remainder of 2. All right. Now I take this column of remainders and I make it fall over to the right, and that gives me the value 2, 1, 2, 0, 0, 1, 2, base 3. So to convert, we have 5306 in base 7 and has shown that to be equivalent to 2120012 base 3. So that method can be used to convert between any pair of arbitrary bases. But we've also shown today that if the bases that you're converting between have a common root, then you can convert easily by going to the common root first. If one of the two bases that you're converting between happens to be the common root, it's even better because then you don't have to convert to the common root initially. You can just make the transition directly.